Okay, today, because we have outreach activities, the audience is small, but thank you for being here. And thank you, Sophia, for coming and visit us. She did her studies in the University of Massachusetts, graduate studies, and then PhD, and then she moved to Edinburgh, where she is doing now a postdoc position. And today, she's going to talk us about the feedback in a very general way. So, please, all yours.
Thank you. So, as you just heard, I'm a postdoc at the University of Edinburgh. I study feedback, and I'm going to talk to you today about some tools that I've been working on developing to improve the way that we learn about feedback from spectra. So I tend to take an extragalactic perspective, but just for context, feedback is something that happens in all parts of astronomy on all sorts of spatial scales. Over here, I'm showing a beautiful biconical outflow with a wind, and there's a jet. That's not an AGN. That's a young stellar object. That's a T-Tauri star. But the physics that goes on here is very similar to the physics that we would see going on a much larger scale, say an AGN that's launching winds and jets in the central kiloparsec of the galaxy. I'm showing over here something similar. This is an AGN with, say, a double cone. There's some sort of a rotating disk, and it's launching things on a much larger scale. So here we're looking at scales that are maybe on the order of thousands of astronomical units. Here we're looking at scales of thousands of parsecs. But we see that feedback is really critical in shaping both of these systems. And so it's really something that it's important to have the appropriate tool set to try to understand. What I care about in terms of the work that I do is really trying to understand the baryon cycle and what that means about how galaxies develop the properties they have over cosmic time. So here's sort of the canonical picture from the Tomlinson review back in 2017, just almost 10 years ago now. It shows the various different modes of feedback that go on, so you can have some sort of gentle or gradual ejection of gas that doesn't really make it out of the gravitational potential. It ends up in a certain galactic medium, and then as it cools down, it will precipitate back down into the galaxy. And then you can also create pristine gas from the intergalactic medium. But sometimes your feedback is just so intense that you just completely eject things from gravitational potential and you lose it entirely. And so understanding what is involved with driving these different modes of feedback and the impact that that has on the host galaxy is really important. One of the implications of this is a scaling relation known as the mass metallicity relation, which is the correlation between the metals that we see in a galaxy, the amount of metals we see in a galaxy, and the buildup of stellar mass in that galaxy. This is not how it's typically shown. This is a little bit more complicated, but this is essentially showing what the ISM metallicity looks like compared to what is embedded or entrained in outflows. The outflows are in the numerator, the metallicity of the ambient gas in the galaxy is in the denominator. This is this metal living thing here. And so this is plotted as a function of stellar mass. And this is showing us that the outflows are much more metal rich relative to their host galaxy in the very early stages of galaxy evolution, when stellar mass assembly hasn't really completely taken up. And that this evolves as galaxies evolve. So your feedback in the early stages of galaxy evolution is important. However, you can see that there aren't a lot of data points in here. It's a very difficult sort of a measurement to make unless you have really great, pristine, deep spectra or the right tools to try to learn about these things. And you can see that there are huge parts of the parameter space that are not well sampled at all. Like, for instance, this most of the dwarf galaxy region. So we've got one data point really between sort of very, very, very the smallest galaxies that we know and sort of the upper limit to the dwarf galaxy region. Now, there are different ways that we can generate feedback in galaxies. This is sort of the canonical M82 system. So we've got these beautiful outflows that are almost galaxy-wide. Here's this X-ray core. We've got these streams of cooler gas around the edges and the periphery and entrained in this hot fluid. You can even see this on Feedback on smaller scales. This is superstar cluster, Mercurian 71. Here, we also see very, very rapid winds, cool things entrained in a hot gas, but the driving mechanisms are different. So over here, we're seeing supernovae that have exploded and are injecting energy, instantaneously accelerating gas up to really high velocities. Whereas over here, the process is a little bit more gradual, so you can get up to really high velocities, but radiation pressure is imparting momentum to the gas on much longer time scales. We can see something similar in EGN. So EGN can launch jets that are larger scales than their entire galaxy. These can drive shocks, and these shocks can then expand like a hot fluid. And so this is one form of feedback that we would expect to see from EGN. You can also get winds that are launched from the accretion disk, like in this system here, which is more on the smaller, like somewhat kiloparsec scale, where you have radiation pressure or shocks from rapidly accelerated winds from the accretion disk that are driving sort of smaller scale winds in these systems. And so you can get between supernovae and radiated winds from stellar clusters, and then these different mechanisms for EGN. There are different ways to shape galaxies at different stages in their evolution. So the question is, what happens when and how? So which driving mechanisms are important, and how do we tease that out? So one of the things that has sort of motivated the work that I'm doing is the fact that in some galaxies, we see some really bizarre emission lines. So some of the earliest objects that were identified were ones like Mercurian 996, where you've got this really bright nitrogen-3 line here, which is very strange. We've got helium-2, which is typically only seen in things like EGN. This is a starburst galaxy. And we've got these really, really distinct Wolf-Rayet star signatures here. But also nitrogen-1 and oxygen-1 here that are really strong tracers of X-rays. X-rays from what? I'm going to leave that as an open question for now, but you don't usually get these very neutral looking species unless you've got appreciable K-shell ionization of neutral oxygen and nitrogen. And so that's really weird. People have started invoking fine-tuned chemical evolution models to try to explain these things at high redshift, to try to come up with some sort of an explanation as to why we might see, an overabundance of, say, nitrogen in this nitrogen-3. But that requires invoking some very, very carefully tuned star formation histories. And anytime we start fine-tuning models to try to explain our observations, we should start to become uncomfortable, because that means that we have to pick a very, very unique, precise scenario in order to explain what we see. And that shouldn't sit well with us unless it's something that's readily extensible to a lot of objects where we would expect to see an identical sort of star formation history. So we need some sort of a unifying interpretation of what's going on in systems like this. And so people have been starting to think about that. Are they all EGN? Are they all like weird density stratified systems? So for me, I've been thinking about shocks, and so I thought, well, maybe there's a way to interpret these as being shock-dominated systems. So as a crash course in shocks, for those of you who haven't spent a lot of time thinking about shocks, or it's been a while since grad school, here's a basic layout of what these look like. So this is sort of what your ambient gas would be. We call this the precursors. This is gas that is pre-shock. This is typical nebular conditions, densities, ionization structure, etc. There's ionizing radiation that comes out from the shock front and creates a sort of H2 region. Depending on the velocity of the shock, this can look a little bit more like almost like a stellar radiation field, but it can also mimic an AGN if it's a very fast shock. You can get a lot of X-rays. At this shock discontinuity, you get adiabatic compression and heating of the gas. So you can get rapid heating from this sort of typical 10 to the 4 Kelvin up to the 10 to the 6, 10 to the 7, depending on the shock velocity. And you get factor 4 compression. And then as this gas cools back down towards more equilibrium conditions, you get nearly isothermal gas compression, which increases the gas density by a factor of 10 or even 100. Now there's also X-rays coming out of this hot gas as it's cooling that sustains a sort of photonized region in the wake, but it's weak relative to the precursor in part because the gas in this wake, the sort of post-cursor, is much more dense, and so it absorbs a lot more ionizing photons, and so this sort of mini H2 region ended up getting kind of stunted or suppressed. So that's what a shock is in a very simplistic sense. Shocks can dominate emergent spectra, so even though we tend to think of shocks as being relatively weak phenomena, and relative to, say, photonization, there are examples like M82 or more extreme NGC 39. These systems, the emergent spectrum is almost entirely dominated by the shock. So we know that this can happen at low redshift, and so I looked at a set of objects at higher redshift to try to understand whether this could also be the case there. Now, there's some evidence that this could be the case before we even start looking at models. There are galaxies that, as I said before, have these bright ionization lines like nitrogen-4, these nitrogen-3 lines also that are high density. You can't really produce appreciable nitrogen-4 from stars alone, and so that tells us already that something else must be happening. We see these broad emission lines that tells us that there's something kinematically weird going on in these sorts of systems, both at low redshift. This is Markarian 996, and this is a high redshift galaxy with a long name that I can't remember. It's just a jumble of letters and numbers. But this tells us that there's ongoing feedback of some sort, and we know that it's specifically feedback because we see these broad components in the forbidden lines. This can't be coming from, say, the broad line reach of an AGN. This has to be some sort of a galactic flow. We also see evidence in a lot of these systems at low and high redshift of very dense gas, at least in higher ionization states, as evidence from, say, for instance, the carbon-3 doublet flux ratio, also from the nitrogen-3 lines and the nitrogen-4 flux ratio. And so this tells us that there's some high density gas, but then the low ionization lines seem to suggest a low density gas. And this could be evidence that there's a combination of a shock plus a precursor. So to address this, I've put together a suite of homogenized ionization models. So these use the same exact atomic data, abundance patterns, dust treatment software to make all the predictions. And so there are no systematics, like, say, comparing one shock code to a different photonization code that you would get from, say, running cloudy and versus mappings. And so here all the systematics have been accounted for. Just as an example of how thinking about ionization diagnostics might work, here these are stellar ionizing SEDs. Even the most extreme scenarios, you can't really produce much above the helium-2 ionization threshold here. And so lines that are associated with these ionization potentials up here are going to be more closely associated with AGN or shocks. But shocks can mimic an AGN ionizing SED. So this is the emergent shock spectrum here in brief. Usually publicly available, so if you're interested in using models, please do so. But here I'm going to show some examples of the power of using these to try to tease out the presence of feedback in action. So for galaxies at low and high redshift, so for low redshift, I've got Markarian 996 that I've mentioned a few times, the superstar cluster, Markarian 71, the sunburst arc, which is at redshift 2.4, and then galaxies at high redshift with really bright nitrogen lines. And so when we compare shock models and these other models that have all been homogeneously processed, when we compare those to the data, we can see that the shock models are the only models under sort of normal nominal conditions that can get anywhere close to reproducing these flux ratios. And so the bright nitrogen lines, nitrogen-4 and nitrogen-3, are most consistent with shock ionization. So this suggests that these systems, both the low redshift ones, sunburst arc or Markarian 996, that these are most likely shock dominated. And so there's evidence here then that these galaxies are being rapidly, they're undergoing some sort of rapid enrichment from Wolf-Rayet stars and such, but it's really feedback that's driving the emergent spectra, not AGN or star formation. Now, in reality, is there some mixture going on? Probably, and that's been slated for future work. But the evidence right now strongly suggests that shocks are indeed at play, both at low and high redshift in galaxies that have these wonky looking flux ratios. There's a really important implication here. So if you account for the shock ionization structure and density effects from gas compression and such, the feedback that these models predict is most consistent with the flux ratios is about 100 to 200 kilometers per second. And that when you compare the implied abundance ratios for those models to what you would get from, say, the direct method, the direct method abundances put you here in this n over O versus over H diagram. But if you do account for all the properties of the shocks and such, you end up over here. So instead of looking like this weird dramatic nitrogen excess that can be an order of magnitude higher than what you would expect, say, for typical empirical trends between these the nitrogen and oxygen abundances, instead you end up well within the dispersion, where you would be more consistent with, say, Wolf-Rayet injection of nitrogen into an outflow. And so this could really resolve this huge discrepancy that we have without needing to invoke any kind of dramatic or fine-tuned chemical evolution scenario. But it also gives us insight into what's going on in galaxies as they are actively undergoing enrichment at a variety of redshifts, both at low and high redshift and in between. There's subsequent evidence for feedback for feedback and shock excitation systems from work that Carla is sitting right there. If you haven't met her, she has found that galaxies with high n over O tend to have higher outflow velocities, and some of these also have higher gas densities. And so we see that some of these systems, including the Sunburst Arc and Arcturus 996, that these galaxies are within the shock regime here. And so this is really strongly suggesting that shocks are indeed responsible for driving the emerging spectra that we see, but also some of the outflow signatures that we see in absorption in the UV. We also see in some of these objects that there are very broad forbidden nebular lines that would not be able to exist in the broadline region of AGN. So this tells us that these are almost certainly due to some sort of galactic outflow. The velocities here are order velocity dispersions of over 350 kilometers per second, and that's certainly within the regime for these winds to become supersonic and drive shocks. And so, and that's also consistent with sort of the range of shock velocities that we see here, about 100 to 200 kilometers per second. And so you can very easily get shock excitation from these winds that we see present in the broad lines of these systems. And so we think that this is definitely corroborating evidence for shocks driving what's going on in galaxies, both near and far. But there are some implications beyond just thinking about abundances and just identifying feedback and action. There are additional tracers, so work that Carl and I have been doing to follow up on thinking about nebular diagnostics in the context of feedback. This is actually hot off the press. Carla made this figure. Yes, was that yesterday? Yeah. Where you can see the auroral 4363 line from oxygen that takes is very temperature sensitive and takes a lot more energy to excite. And the 4363, this becomes a temperature sensitive diagnostic. So this axis here is tracing almost purely the gas temperature, and then this axis is looking at essentially the gas temperature relative to the number of ionizing photons that you have available. Now, in some limits, when you get very high gas densities, this also becomes sensitive to the gas density. So if you have shocks that can actually exacerbate the 5007 to 4363 ratio, suppress the ratio, and so you can end up sort of moving in this direction. And so you can see shock models tend to fall over here because of these density effects combined with the ionization effects. And so when we look at galaxies that exhibit really high gas temperatures, this can actually be a way of trying to diagnose feedback, but this also then indicates what this feedback is doing to these systems. And so this feedback is actually having a net heating effect on the gas. So you end up with gas temperatures that are higher than you otherwise would be capable of producing from photoionization alone. And the impact of this is to dramatically increase the photoionization feedback, because when you heat gas through photoionization, it's almost like setting off a bomb. You have this dramatic increase in the pressure in an H2 region through increasing the temperature while the density remains fixed, or in the case of a shock, actually gets increased. So you can end up with this dramatic overpressurization through processes like shocks, through this excessive gas heating, and that can cause dramatic expansion in systems that otherwise would not be dramatically expanding. And so this exacerbates these effects of overpressurization. We can see similar phenomena in EGN. This is work that I did with Carla and a few other people last fall, where we found that there was a sort of a suppression of the 5007 line relative to 4363 in a sample of EGN that is uniquely describable with shocks. EGN models tend to live over here in this box, and galaxies that show sort of excess 4363 relative to 5007 also are uniquely explicable by shocks, which tells us that EGN are doing something to overpressurize their environment, not just through photonization, but also through shocks. So to sum up this part of the work that I've been doing with feedback, shocks are uniquely capable of describing UV bright nitrogen lines, both at high redshift, but also at low redshift and intermediate redshifts. They indicate that feedback is what's driving the emergent spectra, not nitrogen, not extreme nitrogen excess. But there's some considerations we need to make, like for instance, as I mentioned before, line mixtures. So say for instance, you have a star-forming galaxy that's also got shocks going on because you have supernovae going on. Or systems that are undergoing Lyman continuum escape where you have density bending. So it's something that I actively collaborating with people like Gorilla on trying to understand the impact of these sorts of scenarios on the immersion spectra, and what this might be able to tell us about feedback and how it shapes the geometry and conditions of the host galaxy. So I talked about broad emission lines as evidence, corroborating evidence for shocks, but is there something more that we can learn from looking at the kinematics of these lines? So these broad forbidden lines and the presence of younger stellar populations as evidenced by, say, really bright Balmer lines, or in the case of galaxies where we have access to the rest UV, we see also P Cygni line profiles that are indicative of stellar winds, stellar atmospheres that are driving winds that can only be associated with 3 megayear, 5 megayear stellar populations or younger. This tells us there's active ongoing stellar feedback, and that is somehow associated with these broad emission lines. So this is Mercury 996 again. This is another one of those fun alphanumeric codes at high redshift. And you can see that there is this sort of excess tailedness here in these line profiles. But if we're saying that this thing here is an outflow, right, does it make sense to describe it with a formal model that is consistent with stochastic motion due to turbulence or thermal distribution of velocities? And I would argue that that is probably not the best way to go about doing things if we're going to try to learn about what's actually driving this gas. In the past, people have taken this approach of using one or many Gaussians to try to describe the complex kinematics that we see in galaxies and EGN. So over here is an example of early work in doing this sort of Gaussian decomposition to sort of suss out the details of the kinematics in very complicated systems. People also relied on a more empirical system. This is W20. This is the earliest version of W80. People have since renamed this W80 because this is the 10 and 90 percentile confidence intervals on the flux distribution design profile. And so where these confidence intervals correspond to velocities, this will tell us something about, sort of empirically, about the velocity distribution of this gas in the outflow, as opposed to doing this Gaussian decomposition where you would get multiple velocity components that you would need to use to try to think about what's going on with the kinematics of the gas. People have come up with some more novel approaches to try to understand the physics of the driving of these systems. Over here, I'm showing work that Lena Komorova did for the low redshift Lyman continuum survey that some people here have been associated with. So she fit Hauer laws. This is a heuristic model, but it's largely successful in describing the shape of these the wings of these line profiles, and she found that the slope of the blue wing tends to be a little bit different than the slope of the red wing in most cases, and this is reflective potentially of geometry, but also that the overall slope of these wings tends to change as a function of line and continuum escape, and that may be associated with the sort of feedback that's going on in different systems and galaxies. Mark Krumholtz and collaborators put together a more sophisticated system with a lot of physics where they've got things like clumping factors and the different conservations of, say, surface area versus solid angle versus no conservation, and then an isothermal potential or a point source potential that the flow comes out of. And so you can turn a lot of knobs in these to get very unique looking emergent line profiles. And that's what these look like here. So here's so the conservation of solid angle, conservation of surface area of like clouds that are being driven, point source, gravitational potential, isothermal, and you can see that there may be some degeneracies here in these H alpha profiles, but there is something that might be able to tell us about the driving physics of these galactic outflows. However, these sorts of models are very cumbersome, so while they can teach you about the physics in more detail than the more heuristic approach over here from Komarova and collaborators, including myself, I was involved with this. It's really difficult to try to use this to actually fit data, to try to model data, because there are just so many parameters and there's no readily implemented code to try to actually turn this into something into a tool to try to model data. When we do detailed deep spectroscopy in a spatially resolved sense of systems of galaxies that have flows, we do see evidence for, say, density gradients, for strange geometries, not isotropic or other directed geometries like this conical system here. In AGN, you see evidence for velocity profiles that are radially distributed across a flow. And so this might actually be able to help us think about or inform the sort of decisions that we make when we're trying to model a line profile. And so I've done just that. I've put together a public code for physically motivated line profiles. And so this takes principles of the density gradient, the velocity gradient, and the directed anisotropy or isotropy of a flow, and integrated those all together to predict absorption and emission line profiles. It's publicly available, it's on GitHub, you can pip install it so you don't have to even think about GitHub. The objective here is to allow this, to use this to learn about the underlying driving physics of outflows and learn about the feedback in systems that exhibit these broad line profiles in emission and also in absorption. The basic premise behind how all this works is that, so you have, say, some velocity fields, some velocity gradient. Here, if you have very rapid acceleration like this dark line, you would expect most of your gas to persist out at higher velocities. Some of that gets reprojected to lower velocities along line of sight, but in general, you would have a lot of gas at high velocities, and so you end up with this sort of broader, sort of fatter, gordita. Is that how you can say it? Gordita, line profile. Whereas if you've got a gradual slow acceleration, this rapid acceleration would be like energy injection. You have an explosion, a supernova going off. You've got shocks. You've got some sort of really hot, expanding gas, and that's causing this rapid acceleration. So you would expect this sort of broader looking line to be associated with sort of ram pressure or thermal driving of a gas. The slow acceleration, you have less gas at high velocities, more gas at low velocities, and so you end up with a more narrow peaked line profile. That looks more like this dashed line here. And this will be associated with mechanisms like optically thick radiation pressure, where you're slowly imparting momentum to your gas, and so the flow very gradually accelerates out to high velocities. Now these two different line profiles, they have the same intrinsic mass and same intrinsic flux and the same terminal velocity, but the driving mechanisms are different, so they produce a unique shape to the line profile. And this allows us to learn something about what's going on with the driving physics. There's also a density profile. This is essentially just a radial geometric term. And this can tell us about whether the feedback has been happening sort of continuously or if it's sort of a one and done event. And so if we have sort of continuous injection of energy or momentum, you would expect a smooth gas distribution throughout your flow if you're averaging over many clouds. If you have sort of a one and done event where you've had, say, an explosion with a supernova, or you've driven a super bubble through the convergence of many stellar winds into a sort of a single event where you have one bubble that's expanding, you would expect something that looks a little bit more like this if you're, say, taking a cross section. And so you can parameterize these through, say, a power law or an exponential gradient. Here you can use a Gaussian, a boxcar, or some other little thin slice. And these can produce unique line profiles. And so in the context of a wind or continuous distribution, you get something that has these sort of power law looking wings like we've seen empirically from those models that I showed you earlier. Whereas if we have a box, due to the fact that the projected velocity slice ends up having the same solid angle slice, you end up with a continuous distribution of uniform distribution of flux, and you end up with a box that looks like this. And so if you see something that's more box-like in your line profile, like we see in systems like Mercury 1986, which is how he's working with, you would expect to see, you would expect that to be consistent with bubbles. You can also introduce some anisotropy into your system. I realize I'm adding more and more parameters to my models now. These things are getting more complex, but I promise there's actually a lot less degeneracy than it looks, and you can use this to learn things from line profiles. I'll get there in a minute, but when you have anisotropies, that they end up presenting as anisotropies in the line profile. So if you are directed towards the observer and away from the observer, you lose all of the flux from the system, the part of the flow that would have been projected onto the plane of the sky. And so you lose the core of your emission line here and here. And if you are projected along the plane of the sky and not towards the observer, you end up losing more of your wings. And so you can end up learning something about the anisotropy of the line profile, depending on how things are projected. Here, whether you have a core and not much in the way of wings, or if you have no core and so these sort of lopsided wings. And the prevalence of that anisotropy in the line profile tracks with how anisotropic this is. So if you're very directed, very collimated, so low opening angle, you end up with much bigger gap here in the middle. You lose a lot more of your low velocity flux. So let's get on to some data, shall we? So not just thinking in model parameter space. This is an EGN with a known outflow. This is MGC 2992. This is a beautiful Muse cube of the oxygen-3 flux. You can see this nice butterfly-looking thing in the line flux. It's got these cones that look like this. There's some sort of a velocity associated with this, so we think this is an outflow. It's got evidence for hot expanding gas. It's got coincident with these cones in oxygen-3, there are also radial lobes, which tells us that there's some sort of a hot gas that has accelerated charged particles in it, and so something must be going on with accelerating this gas and outflow, probably associated with ram pressure. Because we know a priori that we can determine both the driving mechanism from the presence of ram pressure tracers and from the presence of this clear geometry in the oxygen-3, this is really a great test bed to see if the model actually works. Because you can put together whatever toy model you want, but does it actually tell you what you want it to tell you? And so what I've done is I've taken a cube, an IFU cube, and I've integrated the whole thing and treated it like a single spatially unresolved spectrum. And then I've gone and I've fit it with my code, with outlines, allowing there to be an anisotropy in the geometry, and just allowing it to vary freely across the parameter space. So pretending that I know nothing about the geometry, and that I know nothing about the driving mechanism, to see if I can recover what we think we already know about this system. And so so I've done this fit involved with the line spread function, and of course I've got several parameters, so it's sort of conceivable that I would recover the line flux because I have enough wiggle room in parameter space to do so. But is this meaningful? Is this something that has actually taught us something useful? Have we actually got good constraints? And the short answer is yes. So there are very few degeneracies between the parameters. So if you look at the corner plot, and I'm going to show you that here because it's big and messy, but the parameters are relatively well constrained. And when we compare the geometry that we've learned from the asymmetries in these line profile wings to what we see in the IFU cube, they agree, which is really exciting because it tells us that we can learn about the geometry of outflows through spatially integrated spectra at a fraction of the cost that would take with an expensive IFU observation. And so we can start applying this sort of a method from the line profile models to larger samples, massively multiplex surveys like DESI or Foremost that's coming online soon, or Weave, if it ever happens. So we can actually really start constraining how collimated these flows are and how directed they are and things like that. So we actually can place large statistical constraints on large samples of galaxies. We start comparing EGN and starburst to see which one might have a larger impact on its host galaxy. We also find that there is the velocity field inferred from the fit is consistent with ram pressure. And this was not imposed a priori. The model just converged on this during the fit. And so this is really compelling because this tells us also that we don't need to go point radio telescopes at this or X-ray telescopes at this to try to learn about the driving mechanisms. We can also tease that information out of the emission lines. And so we can learn just from modeling just the oxygen 3 doublet. We can learn about the geometry of the system and the driving mechanisms. And so this is very, very powerful. This is not something that's only usable on galactic scales, though, and it's not only usable for HEN. It can be used for other systems. So working with Carla here, Carla's got a very wonderful set of observations of the whole of NGC 5471, which is a relatively low metallicity H2 region. It's SMC metallicity-ish, and it's got these different star clusters. There's not B, not C, and not A. And they all have slightly different ages, which make this a really great laboratory for understanding stellar feedback and how it shapes H2 regions. So this knot A is a 30 Doradus analog. It's about the same mass and age as 30 Doradus, but it's at much lower metallicity, so a factor of 2 lower metallicity, which allows us to really probe the effects of metallicity on the early stages of stellar feedback in superstar clusters, which has ramifications for understanding chemical enrichment timescales and also how superstar clusters can impact dwarf galaxies at large. And so just as a part of this test example, looking at knot A, Carla did an extraction of the spectrum, and I looked at just the sulfur 2 doublet. The sulfur 2 doublet is density sensitive, so the ratio of the flux in this line relative to this line tells you something about the density of the gas. And so right away, you can see just by comparing, if you look at it closely enough, you can see the flux in the wings is very similar across both lines, but the flux in the line core is a little bit different. So that might suggest that there's a difference in the gas density between sort of the wind, the outflowing gas, and the sort of central static gas that's not being accelerated as a part of the outflow. So I've modeled these lines with outlines, and let's see what we've learned. So I went in and I allowed there to be anisotropies, but the models kept preferring opening angles that were a full sphere. So I've stuck with a sphere as my assumption. and then just simple continuous flow and basic wind theory velocity gradients. And from the results, we see that the wind is sweeping up materials, so the gradient indicates that you have more mass at higher velocities than you would get from pure mass conservation, so that there's been some sweeping up of material. We also find a really weak velocity gradient. And so this weak velocity gradient strongly indicates radiation pressure. So you cannot produce this sort of velocity, these sort of wings here like this with ram pressure or some similar phenomenon like cosmic ray driving. This has to be radiation pressure driving. However, the ratio of the narrow components indicates gas densities of about 10, maybe 100 parts per cubic centimeter. The broad components, the ratio here is much closer to the critical density. So that's where the collisional suppression or depopulation of the excited states is similar to the radiative depopulation of the states. And so you start to lose flux from this line relative to this line. And that means that these, the outflowing gas is much more consistent with very high density, much higher density. So closer to 1,000 parts per cubic centimeter. And so that indicates anywhere from 10 to 100 times higher densities in the flow than in the narrow component. Now, this is all isolated within a single superstar cluster. So the only way to produce this sort of contrast in density is if you had something that can dramatically compress the gas from something that's, say, maybe 10 or 100 parts per cubic centimeter up to 1,000. And the only way you can do that is through shocks. And, but if you have a shock happen, you remember from that cartoon I showed you at the very beginning of the talk, when this shock happens, the gas compression happens, but you also have gas heating. And so you would expect a buildup of a hot X-ray bubble of gas within the superstar cluster. And that bubble should expand and it should accelerate the wind. We do not see evidence of that here. We see evidence only for radiative driving in this line profile, which means that the X-ray gas is not exerting a force on the flow to accelerate it up to high velocities very quickly, which means it has to escape. And so what these line profiles tell us from the presence of this density contrast and from the slope of the velocity field, this tells us that there's some sort of a patchy H2 region where it's isotropically patchy. We have this bleed out of escaping hot gas that was produced from shocks as this gas accelerated from stellar winds. But radiation pressure continues to accelerate these winds out in a continuous flow, sweeping up material, and it's the radiation pressure that's driving the superwind. We've learned all of this just from the sulfur 2 doublet. So if we're very careful about how we model these emission lines, we can really learn a lot more than if we just throw as many Gaussians as we can at it until it sticks. There's a time and a place for doing the Gaussian modeling, and that can help us tease out the presence of broad components that might not be visible by eye. But then follow-up modeling through this sort of detailed analysis by getting out these broad wings from a physically motivated model can tell us something much more detailed about what's going on in these sorts of systems. And so similar results were found through looking at 30 Doradus. People pointed X-ray telescopes and radio telescopes and such at 30 Doradus, and they found a very similar system where they have bleed out of the X-ray gas as it escapes. But they did this through really expensive observations where they looked at the superstar cluster and they saw the X-ray gas escaping directly. So we know that this can happen. It's a system that people have seen at higher metallicities. But you can learn about these sorts of things. You can do follow-up observations, of course, but you don't need to in order to infer that this is what's going on. I'm going to skip this object for time and skip over to this object, which is part of the low redshift Lyman continuum survey, which was the subject of my dissertation. This object is sort of about LMC this object is LMC metallicities that's leaking ionizing photons at a prodigious rate. So we estimate that about 20% of the ionizing photons, 10 to 20% of the ionizing photons that are produced in this galaxy escape into the intergalactic medium. Not just into the intergalactic medium, but they made it all the way to HST's detector when we measured them. And so something has to be driving the escape of those ionizing photons. That has really dramatic implications for how we understand the reionization of the universe. So one of the things that I'm excited about working on with people here and at Granada, so specifically Ricardo Emery, Carla Ariano, and Juan Antonio here, is looking at how feedback shapes line continuum escape. So here I'm showing the action 3 doublet, and I've thrown outlines at it to model it to see what we can learn. And the line profile strongly favors an anisotropy in the driving in the geometry of the outflow. So it's directed, and it implies a somewhat gradual acceleration of the gas that is consistent with dusty radiation pressure. And the flow is mass conserving. So whatever got lodged out, it's not sweeping up additional material, but it is conserving its mass. So it's just continuing to accelerate. And that will likely then carry it out into the CGM, maybe even get ejected into the intergalactic medium. So we've got extreme radiation pressure that's driving a wind that's up to over 1,000 kilometers per second. But it is directed, and it is launched, meaning that we don't see any evidence for velocities that are below 100 kilometers per second, which means either there's some sort of a launching velocity at the base of the outflow in the superstar clusters in this system, or the feedback has stopped. So it turned on, it was driving a flow, and that flow is persisting, but it's not being driven any longer. So there isn't material being injected into the continuous band. And so I'm looking forward to expanding this to a larger sample of galaxies for which we've got nice, pristine, high-resolution spectra. So future work is going to involve this follow-up on line continuum escape, further work with Carla Ariano on the other clusters in NGC 5471, but I'm also expanding my work to look at broad absorption line quasars, specifically what's going on with the carbon-4 absorption troughs, because we can see variations in the absorption troughs as a function of ionization parameter in quasars. And so that's really weird, and I'm interested in knowing if that has something to do with the driving mechanisms at play in these systems. The code is publicly available again, but there are improvements that I'm planning to implement. I do maintain it, so if you are using it and run into any issues, if you find a bug or something, I'm more than happy to push fixes and such. I'm going to add some more support for different aperture corrections for spectroscopy, in-house line spread function corrections, some effects of turbulence, and additional physics like dust extinction of emission throughout the outfit. Thank you.
Thank you very much, Sophia. Very nice talk. Question? Sayani?
Hi. Oh, thank you. Well, I come from the stellar and star cluster background. 0, 0, 0, 0, knowledge galaxies. I have a question in the where you show the 2 bits residues with residues. This one, yeah.
Yeah.
I don't know. Would you mind commenting more about the residuals?
The residuals here. Mm-hmm. Yeah, so this is within the noise of the continuum. The residuals here, this label got cut off. It should be a %. But so the fluctuations in the residuals are consistent with the noise in the continuum that we would see, say, like over here outside of the line. So here and over here where we don't have emission signatures, we see noise that's comparable to the noise in the fluctuations in the residuals. So we think that that's due almost purely to just noise in the observation.
Okay, I mean, did you try to correlate it with something? Or model the residuals, I don't know how it works.
No, I didn't do anything to try to model all of those.
Oh, thank you.
More questions? I have some. Can you go back to the N overall abundances? This is a very interesting result because it's one of the, so in the literature, they are interpreting all these high receive objects like nitrogen loud galaxies and so on. So this suggests that this might be a misinterpretation, no? Because the abundances, when you take into account excitation by shocks, might be much closer to the local universe ones. Is there a way to, so this is the prediction for the optical lines. Would the effect of shocks be also the same in infrared lines? For example, the nitrogen 3 and oxygen 3 lines in the far infrared?
I have not done anything with the far infrared. I made predictions, so those lines are predicted from the models, but I haven't tested them against the FIR lines. But that's a good idea because the FIR lines are really density sensitive. So that would
Yeah, so I don't know if but that could be, adding those lines could be could help to understand if they discriminate between also if they are as affected as the ultraviolet lines or the optical lines or not by shocks.
Yeah, I mean that's a really good question. The answer, but
it's a comment. It's not that. Also, there is this mission Prima that it's. Well, I don't know if it's approved but it's under study and there should be say if it goes ahead or not in these months. So that would be a very nice science case for Prima, at least for the local universe. I think they cannot measure these lines very far away, but.
I mean, there are certainly local galaxies that show bright nitrogen lines that we can't explain with regular stellar top models. So, yeah, there are a lot of reasons why I think we should get Prima, and this just adds to that list.
I have also a question about so in the diagrams, the diagnostic using the auroral line of oxygen and H gamma. So here the very high ratios of the auroral over H gamma can be reached, and also very low, the 5007 against the aurora can be reached because of the effect of shocks. But these ratios, they at least the one on the left, they use it to distinguish AGN from star formation. So this means that if you have strong shocks in a star-forming galaxy, you could move the point to the AGN domain.
So the EGN models, which are the orange points here, the EGN would fall above this dashed line, more or less. Whereas shocks tend to live over here to the left. So if you have a shock starburst composite, that would push your flux ratios in this direction.
Okay.
Not this direction. Is there a little bit of excess up here? Maybe, yeah, but I think the effect would be largely just suppressed by this.
But
Okay.
But also it's important to put the context observations, right? Because the circles are high-redshift galaxies and the crosses are local star-forming galaxies. Since there you see something is happening with these very high, with high-redshift galaxies. So we don't understand well how to explain the very high temperatures of that. So AGNs from the paper of Masolari, they do like this, not like how the AGNs can just, well, for the models, I don't know the condition of the models. But in this case, the models are from Sophia, and they can also, the models can cover the similar ratio from Masolari. So we are adding the shocks things. They probably explain that, but discussing with Sophia is probably the shocks could be just a percentage. You see, probably pushing something, but we don't know if really.
And adding the kinematics, for example, I don't know, the full width of the lines to this plot, do you expect some dependence on the, for example, the line width with the position in this diagram?
I would expect, because there would be a gradient in shock velocity, so it is maybe a little counterintuitive, but higher shock velocities actually get you closer to the star forming or EGN regime. That's because the emergent spectrum from the shock is dominated by the precursor, so you don't have any of the density effects that you would otherwise expect. So there's sort of like a sweet spot when you're at like maybe 100, 200 kilometers per second that push you towards the extreme in this direction. So it would be interesting to see if we're in that sort of sweet spot velocity space. Where
Okay, so when the precursor dominates, you don't see such a strong.
right, because the precursor is.
It's not. Okay, and the temperature distribution. This is a more basic question, but the temperature distribution of the electrons heated by the shocks, it's thermalized normally, or you expect like a tail of high velocity electrons? Is Maxwellian or
So
it
I
can
assumed Maxwellian in my models. I did not do anything like a kappa distribution. That is the thing I could follow up on. The gas is sufficiently dense that it does rapidly thermalize relative to the time scale of the shock. So I don't anticipate that it's an issue.
Okay. And also another question I had is in the high ionization lines, they come from the compressed part of the shock, so you would expect higher densities for.
Depends on whether you're precursor dominated.
Okay.
So if you're in the precursor dominated regime, your ionization lines are really just basically like EGN coronal lines.
Okay.
But if you are not precursor dominated, then your ionization lines would come from.
Okay. And the last question I had is about the little red dots. Have you compared or think about how outlines could interpret the profiles they see so for context, the little red dots, they have broad lines, for example, in H alpha, but they found that the broad component in logarithm scale, it's triangular. No? So they have exponential line wings, and at the beginning they interpret that as kinetic broadening. So they were using that to measure black hole masses, and there is other groups proposing that broadening is not due to the kinematics, but it's due to scattering of electrons. The medium is very dense, so you see very broad lines, not because the gas is moving fast, but because of scattering.
Yeah, so I've talked to people who have done more sophisticated modeling of little red dots, specifically the Soroka team. So without lines, I would be able to generate an intrinsic wind profile, but that would need to get processed then through a scattering medium. So there would need to be like an extra step added in on top of what that lines generates. And I'm not entirely convinced that it would be straightforward enough to just take outlines and then convolve it with something, because the outflow itself is part of the dense medium, right? The sort of the understanding is that you have this very thick, it's almost like a gray body where it like has a thermal emission component, but then it also reprocesses lines. It moves, but yeah, I don't know. The red dots are complicated. It's a great question. I've thought about it, and it's the shorter answer is.
It's okay. It's a complicated debate.
That's a good question, though. I'm glad that people think.
Also about outlines, I'm not an expert in this, but I find it amazing that you can get so much information about the geometry of the outflow just from the integrated spectrum. So what about the degeneracies? You promised to show the corner plot.
Yeah, so I was a bad scientist and did not put the corner plot in my talk. I can bring it up for you. Archive. So the corner. Yes, so the corner is here. And so in terms of degeneracies, the major degeneracy, and this is something that I see in a lot of my fits to a lot of different systems, is here. It's this is the slope of the density profile, the density distribution, and this is the terminal velocity. So if you imagine if you make your density profile very steep so that you have very little flux at high velocity, then you might infer a much higher terminal velocity in the wind. So there is degeneracy here, but in a lot of cases, I don't see the same sort of degeneracy that you might expect across the parameters. So a lot of them just look like blobs like this. Sometimes they're double peaked, but yeah. Is that helpful? Yeah, I was really surprised by this. I get the degeneracy question a lot, so I should have had this in my talk. But I was really astounded that it came out so cleanly, just because there are a lot of parameters here. And the first time I plotted up the results from this and compared it to the IFU map of the line flux, I actually like gasped out loud. Carla was in the office and she's like, "What happened?" And yeah, it works. So I was really quite surprised, but very happy. So I think.
Thanks. More questions? If not, let's thank Sophia again. You're dismissed.